Have you noticed the massive buzz around quantum computing lately? I mean, it sounds like something straight out of a sci-fi movie, right? But here is the very first thing you need to know. You absolutely do not need a PhD in theoretical physics to understand how it's going to completely change our lives.
So, welcome to today's explainer, the subatomic toolkit, demystifying quantum technology. Okay, let's dive right into this. The core premise we're unpacking today is that quantum tech is actually this incredibly diverse toolkit. It utilizes the bizarre, almost magic-like rules of the subatomic world to completely reshape our reality. And, spoiler alert, it is about so much more than just building really fast calculators.
Here is our roadmap for making sense of it all. First, we'll look beyond just quantum computing. Then, quantum sensing for extreme precision. After that, simulation for drug discovery. Then we'll tackle quantum secure communications. And finally, we'll wrap it up with the subatomic big picture. All right, part one, beyond just quantum computing. You know, while those ultra-fast next-generation computers grab all the flashy headlines, and yeah, they are cool, computing is literally just one single facet of a much wider, much more fascinating technological revolution. When we talk about quantum technology, what we are really talking about is using principles from the subatomic world to process information in entirely new ways. It's all about harnessing the laws of nature at the absolute smallest scales. We're talking individual atoms and subatomic particles here, folks. And doing that completely changes how we gather, process, and protect data. Moving to part two, quantum sensing in extreme precision. Let's shift our narrative away from the abstract concepts of computing and look at the physical, tangible world right around us. Quantum sensing is all about measuring our reality with unbelievable, unprecedented precision. And the crazy thing is, this isn't some distant, far-off future concept. It is actually saving lives today. Just think about the MRI scanners in your local hospital. An MRI relies entirely on measuring a specific quantum property of atoms called spin in response to magnetic fields. It's literally a computer measuring a tiny subatomic change to generate those life-saving medical images we all rely on. But of course, the technology is rapidly evolving. And this next part brilliantly illustrates how we're transforming those massive, clunky machines into everyday tools. So on one side, you have traditional room-sized MRI scanners that cost millions of dollars. But on the other side, we have these emerging things called optically pumped magnetometers, or OPMs. By taking advantage of quantum effects like superposition, which is where particles basically exist in multiple states at once, we can measure magnetic fields so precisely that these OPM sensors can actually be used for neural imaging. And the best part? They're small enough to be wearable. I mean, just imagine getting a hyper-accurate brain scan while wearing what essentially looks like a high-tech bicycle helmet. It's wild. Now, another massive breakthrough in this sensing toolkit involves something pretty sparkly: diamonds. Specifically, things called nitrogen vacancy, or NV centers. These are basically tiny, specific defects found naturally or synthetically inside diamonds. And because of their unique subatomic structure, their quantum state is highly, highly sensitive to changes in their surroundings, especially magnetic fields. This extraordinary sensitivity is opening the door for hyper-accurate diagnostic tools in healthcare, and even entirely new, ultra-precise navigation systems that completely bypass the need for GPS. And to wrap up our look at sensing, it's absolutely crucial to note that these tools measure way more than just magnetism. Quantum sensors can act as gravimeters and gyrometers to measure microscopic shifts in acceleration. They capture environmental changes down to the absolute smallest variables, measuring time, temperature, and pressure with the level of accuracy that our traditional classical instruments simply cannot ever hope to achieve. Let's jump into part three, simulation for drug discovery. All right, so we're transitioning from measuring our reality to simulating it. We're stepping into the virtual laboratory of quantum mechanics. If you have ever worked in material science or drug discovery, you know exactly how incredibly laborious the traditional chemical pipeline is. Step one, you have to physically build the chemical compound. Step two, you test it in the real world. Step three, you refine it. This whole process of physical trial and error takes years. And the cost? We're talking millions, sometimes billions of dollars. It is a massive bottleneck for modern medicine. As the team over at Sandbox AQ rightly points out, it's much more convenient to simulate the behavior of that new drug on a computer. But, well, here's the catch. Keeping track of countless individual atoms and molecules using traditional computers, it becomes staggeringly complex very, very quickly. Conventional computers just flat out can't handle the math. But quantum simulation, it acts like a revolutionary cheat code.
By using quantum systems to actually model other quantum systems, like super complex molecular structures, we can predict chemical behavior almost instantly. That saves years and years of physical lab work.
Which brings us to part 4, quantum secure communications.
So here is the crucial vulnerability we need to talk about. With all this incredible new computing power comes a massive, imminent threat to our global data security. Think about our current encryption, that invisible mathematical shield protecting your bank transactions, your private messages, even your home Wi-Fi network. It relies on math problems that are incredibly hard for classical computers to crack. But to an advanced quantum computer, those same problems essentially look like a child's math puzzle. A powerful quantum processor could solve them effortlessly, which would leave our entire global data infrastructure totally exposed.
Now, to combat this, the industry is frantically building a really powerful dual shield. Let's see how this builds out. On the software side, we have post-quantum cryptography, or PQC. These are software and algorithm upgrades designed to run on our current regular computers, but they're mathematically built specifically to resist attacks from quantum computers. Then on the hardware side, we have quantum key distribution, or QKD. This actually leverages quantum effects like entanglement to securely send information. Because of the weird laws of quantum mechanics, if an adversary even tries to intercept or observe that data, the quantum state changes, and that instantly alerts us to the breach. Pretty clever, right?
Finally, part 5, the subatomic big picture. So what does this all mean? How do all these totally disparate elements actually connect? Well, ultimately, the quantum advantage is about so much more than just a really fast computer. It's a dazzling, interconnected ecosystem. We've got extreme precision sensing to measure our physical world, molecular-level simulation to invent completely new materials and life-saving medicines, and unbreakable global security to protect our digital lives. These are real, practical, everyday applications leveraging the deepest laws of nature totally to our benefit.
Which leaves us with this provocative final thought. If harnessing nature's absolute smallest laws can solve our biggest, most complex global challenges, what will we conquer next? Seriously, the quantum revolution isn't decades away. It is already happening right now, all around us, subatomic particle by subatomic particle. Thank you so much for joining me for this explainer. Keep your eyes on the microscopic world because I promise you it's about to change absolutely everything.